I will begin with a word of prayer. Dear Heavenly Father, we thank you for this afternoon. Thank you for the snow partly melting. And we thank you for topology, which is fun. Help us to enjoy it today, Lord. In your name I pray. Amen. Okay, so guys, like I was telling you, I was going to let Bill take us to school here. My brother Bill. So he has a few handouts on different things here. Like, for example, Zermelo-Fraenkel set theory and the axiom of choice. Here he actually has, a set of axioms which sort of give you a more precise account of what the usual set theory encompasses, in as much as the meaning of terms can be understood. Of course, you could take a whole course on these things and cut things more finely. I know Dr. Skimordis has some interest in these sorts of foundational issues. I won't even read them, but as you can see, they're somewhat involved. Now, the axiom of choice, of course, is one of the more famous ones in here, right? And he mentioned some of the this is probably interesting. Historically, some mathematicians have rejected the axiom of choice because it leads to a few counterintuitive results, such as the Zariski paradox, which isn't a paradox in the logical sense, but it's a very odd theorem, which at face value seems like it shouldn't be true. Although I think that is what a paradox is in a logical sense, Bill. A paradox is a seeming contradiction, which isn't really one. Sorry. I shouldn't bite the hand that feeds us. Sorry. On the other hand, most mathematicians just accept the axiom of choice and go on with life. A few reasons for this. Many mathematicians don't know or don't care about foundational issues. Ooh, true though. The axiom of choice is equivalent to things that we really want to be true. For example, all vector spaces have bases. That's something I would like for it to be true. Mm-hmm. Yeah, I want that in math I'm studying. I definitely want that. Given a collection of non-empty sets, it's possible to pick an element out of each of those sets. In fact, this is where the axiom gets its name. Although, kind of, if you look at the paragraph of blah, blah, blah under the axiom 9, which is called choice, I mean, we would read that, and it would take us a few minutes to extract from this idea that it's basically saying what he has a sentence down here, I mean, it's buried in the formalism. The Cartesian product of possibly infinitely many non-empty sets is itself non-empty. Yeah, I would be bothered if I took a Cartesian product of non-empty sets and got something that was empty. I wouldn't like that. That doesn't sound good. No, I don't like that at all. Zorn's lemma, which says a partially ordered set, whatever that means, in which all chains, totally ordered subsets, have upper bounds. There has at least one maximal element. Zorn's lemma gets used as we study higher algebra a lot. And then he has some things to say about consistency, relative consistency. I can't talk. So, all the issues related to the Gödel's theorem and, what's known, what's unknowable. What does Gödel's theorem basically say, Nathan?
Which one?
Which one? The popular one.
The popular one.
Sure.
Essentially, if you have a theory that's strong enough to state basic arithmetical facts, then that theory cannot prove its own consistency.
Right.
I think of Gödel, I think of God itself exists within the thought of itself. Therefore, God exists. Something like that.
I know he was trying to understand what intelligence was, or give some kind of explanation for what is intelligence.
That's cool,
My personal, and this I'm not sure is a really a definition or anything, but I've always felt like whatever intelligence is, it's something that can't be described. I mean, in some sense, being able to describe it, there's some like spark in there that involves independent choice, and if you could somehow constrain it by some kind of descriptive rule, it wouldn't be intelligence.
I saw a pretty convincing
That's just my.
description of intelligence involving Kolmogorov complexity.
Uh-huh.
It's interesting.
Hmm. I've thought about these things before, but not too much of these recently. Let's see, next we have the, and I think that's probably not topology. Sorry. Cantor, Schroeder, Bernstein theorem. Theorem, let A and B be sets such that the, I believe, order of A is less than or equal to the order of B, and the order of B is less than or equal to the order of A, then A equals B. Now, these less than or equal to have to do with I think it has to do with injection, the existence of an injection from one set into the other. We're not actually comparing numbers here per se. I mean, we could be in the finite case, but we don't. We're generally, we're comparing different infinities or something. It's cardinality. And, well, look at that. A proof, which I will not be so foolish as to try to explain to you. I just wanted to give you some reading so that you have a little bit more on these things. All right. So any questions about anything before I get back to business? So basically, work out the homework. Those are nice basic set theory homeworks about how functions behave with sets and such. And then any question Bill puts on a test is going to be a good question. So those are worth working. And some of them will be easy. And some of them will not. But I have looked at those in previous years with other students, and they were interesting. Okay.
Minetti has some stuff on that too. I remember when glancing
Yeah,
over chapter 2, he had stuff about functions and sets like that.
Right. There's,
I think we have problems exactly like this
Yeah,
for reals. Yeah.
Yeah.
Like
That's
one of the
funny.
yeah.
I
think we did
I mean,
that
Yeah,
one.
I think the
What-
entire first homework.
so once you guys get your book, you can just start. I don't want to, restrict you to certain problems. Just start working problems from Minetti once you get it, and give them to me as you get them done, and work the ones that help you understand. True understanding of the book will come from working homework problems with the reading. That's what you got to do, right? So, I would encourage you to do that. Imagine if I taught a calculus course like that. Just do some homework so you can understand. Well, which ones are we supposed to do? Do the ones you need to understand. Okay. They'd be like, yes, there's no homework. But I trust you guys won't do that. All right. So last time we defined a topology, right? So a topology was what? Am I allowed to write all the way to the dotted line, or?
I think so.
It's
Okay.
4:00 p.m.
Uh-oh, I've only got an hour left. Sorry, I misbehaved. So X is space, a set, right? And then the topology, some subset of the power set of X, some family of subsets of X, such that what?
The empty set and the set itself are included.
Right.
The infinite
Right.
union
Any
of all the
collection.
sets is again
Yeah,
an
union.
open set is again open.
Right, union of sets in taken from the topology, right? Are again in tau, right? I mean again in the topology. And finite, right? Finite intersections of open sets are open. And by open, we say U, an element of the topology, is an open set. For a given point set, we can have different topologies, right? So the notion of open, it's it depends on the context, right? Let's see here. You can recast this in terms of closed sets, right? You could actually define a topology in terms of the closed sets as well. If I give an account for every set that's closed, right? Think about this. If I say, V an element, listen to me, V a subset of X is closed. Let's say if V is an element, I guess I need some other letter, I don't know. I'm going to use tau for the open sets. Let's call, I don't even have a good notation for it. I'll call it Pac-Man. I don't really know a standard notation for it.
7.
7, no, so I use 7. I think Joe was in here earlier microwaving pancakes. I smell pancakes when I got in here. It's really strong. Somebody microwaved some pancakes in here earlier. I'm starting to think I need to lock my door. It was thick. I was like, it made me hungry. I had to go get something to eat. But okay, so that's closed. Suppose you give the collection of closed sets, right? And then you could define U is open if what? U is equal to the complement of X by some V for some V in Pac-Man. Some closed set in the set of all closed sets. So what axioms would you need to give for this Pac-Man? Like what conditions would we need on the set of all closed sets in order for us to reproduce the definitions for open sets as we have them?
The empty set and X are not in Pac-Man.
I think they are. I think we need.
Or I guess they are.
They are. I think we do.
Sorry.
We need this and this are in Pac-Man because then
you could
X
get
complement the empty set is X, and the empty set complement the whole set is still the empty set.
Yeah.
Right. So that would say that.
Or X complement X. Yeah.
Oh, did I do it wrong?
No, you're good. I was just saying you could also say X complement
Oh yeah,
X.
it really should say X complement X because that's what the logic here, right? My point is that's a closed set, so complement by that's an open set. So this says that X and phi are an element of the topology, which I'm saying this is the topology that's induced from the Pac-Man thing, okay? The open sets corresponding to the closed sets, right? So we definitely need that the empty set and the whole set are closed. What else do we need? That's kind of interesting, by the way. This says for arbitrary topologies, the empty set and the closed set. The empty set and the whole set are closed and open.
Have we really discussed that anywhere? Like, I don't remember discussing that in like advanced calculus. I thought I read in the book that it was like can be elaborated on more when I was reading.
We will talk more about this idea of set being both open and closed as it's connected to the topic of connectedness. Using that word in a both formal and informal way in that sentence. But let's see, the other thing we need arbitrary unions
To be the union
to be open.
of V with any other, or to be closed. Right.
Well, I mean our goal is to get we
Right.
I think we need that if let's say, I'm using V, aren't I? So if we have V alpha such that alpha is an element of some index set, we need that the intersection over alpha in the index set of V alpha is an element of Pac-Man, given that these are closed. So an arbitrary intersection of closed sets should once more be closed. The reason for that is if you consider the complement, right? By that, what is this? What's the rule that relates the complement of an intersection?
It's the union of complements
Right, this is the union over alpha.
of X minus V alpha.
Right. This is called what?
De Morgan.
Yeah, it's one of De Morgan's laws. here written in terms of intersections and unions. And of course we need, I mean, if these are open, right? These are quote unquote open as induced from the closed structure here. So we need that again to be, you know, that has to be an open set. So in order, I mean, so basically you could start with this and say, well, this must be open. De Morgan's law tells me that that's equal to this. Consequently, arbitrary intersections must be closed in view of this, working backwards. Okay, so arbitrary intersections have to be closed. And on the flip side, almost by the same token, what do we need? 3.
Finite unions.
Right, so if we have like V, let's say V1 through Vn, then need the union I equals 1 to n. Vi is again, and once more in Pac-Man, if yeah, finally, of course these in Pac-Man implies the finite union is in Pac-Man, because that in turn would say that the complement by this finite union is what? By De Morgan's law once more.
Finite intersection.
Right, it's the finite intersection I equals 1 to n of x complement Vi. And by the definition of topology stated in terms of open sets, that's a necessary thing. So basically just start with what's necessary for the open sets. If they're coming from complements, you can work backwards by De Morgan's law and discover you need arbitrary intersections to be closed, and you need finite unions to be closed.
For the first part, why did you put tau of Pac-Man when you speak?
Oh, what I'm trying to say is that this is the topology induced from this closed structure. I don't mean, I'm sorry, this is, yeah, this is not the standard use of tau. I'm sorry, you're saying I should say tau of x, right? If
Yeah.
anything. I don't know if did I ever define tau of anything? Did I let?
I don't think so.
I don't think I did. What I was trying to say is that this is the topology which is built from the Pac-Man by complementing, by the definition of whatever's the complement of a closed set is an open set. And vice versa. Is that true? The complement of a all right, where was I? So we had some examples, right? Now this is interesting because, okay, so sometimes it's more convenient to characterize the closed sets than it is to characterize the open sets for certain examples, all right? I think probably the most important example of that type is what's called the Zariski topology, all right? Can I erase this? Oh, I'll wait, it's cool.
Sorry.
No problem. So he's got like a half page on the Zariski topology, which is fine, you know. But you know, what is the idea? Where's the Zariski topology coming from? It's coming from the study of what are called varieties. Interesting factoid about varieties, and I think I told you guys this before, but the word varieties translated from a German word which is also translated manifold. Yeah, so what Riemann wrote as, I don't know the German word, but it has been sometimes translated manifold and other times translated variety. The idea, though, really is abstract geometric space. Now, varieties are, at least the kinds I'm reading about here, affine algebraic varieties. This, by the way, is Invitation to Algebraic Geometry by Smith, and names I can't produce, well, anyway, I'm not going to try to pronounce these names, you can read them. Interesting little book. It's a nice start. It's certainly not the ending point, but they try to explain, at least a little bit intuitively, the notion of variety. And so it goes back to calculus 3. I mean, the variety, so manifold essentially is a parametric viewpoint, you know. We try to parameterize some abstract set by these charts onto it, right? Variety is more built from the equations which define the set. So a variety will be defined by as the common solution set to some set of polynomials. So, oh, here it is. You might have some trouble seeing that from the half page that Manetti has devoted to this topic. Let's see here. So let me just show you a couple of examples of varieties, so you can a little bit better understand this idea. But really, I'm just trying to develop another kind of interesting example of a topology, which is kind of out there. So here's the variety. He says the variety uses a double V. The variety built over the y minus x, so generated from y minus x squared subset of C2. Now, that's the the complex plane, and that's a four-dimensional thing, right? So he just draws the real points. He just looks at the real components of this, basically, and it looks like this. Okay. Here's a more interesting one. The variety of x squared y plus xy squared minus x to the fourth minus y to the fourth, again, as in a fine variety subset of C2. This one's a little bit more exciting. It looks like a, let's see if I can do it right. I fail. Here's another one. The variety built from x squared plus y squared minus z squared in C3. This is the quadratic cone. It looks something like... Now again, you're like, wait a minute, you said it's in C3. That's a 6-dimensional space. What do you mean that's what this is? That's the real part of it, which is 3-dimensional. So we can still kind of visualize these things that can't be visualized in terms of piece of them. All right, so Cn, complex n space. What is that? That's the variety of what? How do you get the whole space? So we're looking at these are the set of points. What we're looking at is the real part of the set of points where this is set equal to 0. So like this is y equals x squared, essentially.
Just the constant function 0?
Exactly, right. So that's included as an example of a variety. The whole thing. How do you get the empty set?
One.
Yep. 1 is not equal to 0. Very good. And you can also get a singleton. How do you get a singleton as a variety? Or an n space. How would you get this one as a variety? Now here's so you guys, the thing that's messing with you, maybe all my examples up to this point have been based on one polynomial. Does this have to be the case though? We can take a union of the common locus of a union of them.
This would be like x minus a1.
Mm-hmm.
Yeah. Or x1 minus a1.
Comma. Yeah.
y1.
X minus a2.
X minus
Comma. You can take a bunch of them. So in order for those all to be 0, that means that x1 is equal to, x1.
x1, x2.
I will eventually get it right, 2n. little bit off the beaten track, but I think it's worth 10 minutes of our time to talk about this to try to understand it a little bit. They have it as an example. So a singleton is a variety. Let's see here. So he says the zero set of a single polynomial in arbitrary dimension is called a hypersurface in Cn. The quadratic cone I drew there is a typical hypersurface. He says the zero set of a linear polynomial is an affine algebraic variety called an affine hyperplane. So for example, an affine hyperplane in C2 would be something like ax plus by. Minus c, I suppose, in our current way of thinking. Of course, that's just a funny way of writing ax plus by equals to c. There's an affine hyperplane in C2. All right. I'm getting to a point here. All right, so we have some sense of you guys starting to understand what a variety is, the common zero set of a finite set of polynomials in Cn. C, it could be C, it could be C2, it could be C3. Now he then explains how SLN C could be. I'm gonna take some of the wind out of his sails here and go on. There's more. I'll just say there's more. All right, getting to it. It's also important to have non-examples. For example, the open ball in Cn, in the Euclidean topology, is not a variety. You can't do that. The set of, if you look at the set of invertible n by n complex matrices, with respect to the usual topology n matrices as we'll define later, that's also not going to be a variety because it's actually an open set. All of these things are closed sets in the sense of Euclidean topology in Cn. All right, so then the question then is, how are these different things related? So basically here's the deal. If I have a variety which is, say, defined by polynomials fi, all right, say from I and I, big I, and I look at the intersection of that with the variety built from polynomials, say f sub j, for j and j, right? That is in fact equal to the variety built from what? Let me make this less mysterious. If we take something like, a sphere. Let me just talk about, let me talk about real varieties for a second, because that's where we're more comfortable. The real varieties are the same idea, just in Rn rather than Cn. Cn is nice because it's complex. Algebra happens there. But this would be something like what? X squared plus y squared plus z squared equals to 1, right? And then if I take this guy, right? Well, I haven't drawn it very well. It would be you can't draw it with any. I'm trying to draw a great circle, badly. Maybe this is y equals to 0, right? So this is, the one variety is the sphere, the other variety is the vertical plane. If you look at their intersection,
It's the variety of the union.
right, exactly, it's the variety of the union. It would be the variety of, in my example, of y, comma, x squared plus y squared plus z squared minus 1. See, that is the intersection of the variety. That's the vertical plane, which would be the y1, and the sphere. Right? What if you What if you wanted to take the union? What if you wanted to take the union of two varieties? How would that work? So here's a stupid example. Suppose I want my graph, I want my function, I want a graph that looks like this. Here's y equals x squared, right? And plus 1, and also the unit circle. I'm going to use implicit plot to make this. How can I do so? Thought about this? Ever think about how to spell your name with an equation?
You're gonna want to have like y minus x squared minus 1 times x squared plus y squared minus 1, right?
Right. You
Equals
just
0.
Because in order for this, all you need is either one of these to be 0 or the other of these to be 0, and so there you have it. So if you want to take the union of varieties, if I would say I want to take the union, I equals 1 to n, of the variety built from, say, f sub I, all I got to do is say, aha, that's simply the variety of the product, I equals 1 to n of fi. Here I'm using the product notation that... Did you take complex?
Nope. I wish I would have, especially after today's AC circuit analysis. I mean, I do. I'm doing completely fine. But
Yeah, come sit in like one of my Calc 2 lectures. Today I did adding angles formulas from imaginary exponentials.
I remember school board is teaching that.
Well, the thing is, you know, I can. So, I don't know. I mean,
You should make like a simplified complex analysis.
yeah, I used to shy away from it because Dr. Kester he was actually against it, and but so there's no one here to stop me. And I actually, I mean, joking aside, it's really a useful technique for remembering trig identities. My goodness. And its use is really, well, I digress. All right, so this shows us that the finite union of varieties is once more a variety C, because this is still a finite polynomial. See, all of a sudden, look at it. So so what you see is that varieties define closed sets. They have the correct structure. The arbitrary intersection, that's basically an arbitrary intersection, is again a variety. And the finite union is again a variety.
And the empty set.
The empty set, the whole set. Bam. We can call varieties closed sets. And doing such defines what's known as the Zariski topology, which of course is important to algebraic geometry. Algebraic geometry being the study of abstract spaces in terms of solution sets. Oh, I think it's so much more than that. But the much more than that I don't really have a clear understanding of. It's one of my lifetime goals to understand algebraic geometry. I just understand pieces. Now there's some really weird stuff here, right? What's open in the Zariski topology?
It's the complements of its sets.
So the Zariski topology is an example of a topology which is not Hausdorff. Now we haven't talked about that before. What's a Hausdorff topology? Basically, Hausdorff says you can separate points with open sets. So like in R2, you can easily see it's Hausdorff, right? With respect to Euclidean topology, if I pick a point P and you pick a point Q, I can just say, oh, I'm going to make my little open set, you know, like that, and you'll make your open set like that. And then we got two open balls. They're separating the points P. They're not intersecting, right? That's all you need. If you can take arbitrary points in your set and find open sets which contain those points and are disjoint, then your space is said to be Hausdorff. The thing about the Zariski topology is the complement to all these curves or planes or whatever, they just go on and on.
Yeah.
And so if you try to separate 2 points, the on and on part always intersect. It's unavoidable. So it's far from Hausdorff. It's an interesting example of a non-Hausdorff topology. All of this I'm expanding on. You can read page 42 of Manetti, where he talks about this for about this far. That's all in there, though. But I thought it would be useful to blow that up a little bit because I think it's interesting. All right? And I think he also has an argument that has an argument about a basis. There's some details in his discussion on page 42 which we haven't done here. All right, move on. Time is wasted. So, what does it mean for a map to be continuous in a topological space? What do we mean by continuous map?
The inverse image of an open set is also an open set with a function.
The inverse image of an open set is, oh yeah, right. So here's the definition. And you can actually see where this definition came from if you just look at the epsilon delta definition in the metric sense. If you really look at that, what it's saying is that the inverse image of an open set is open. I mean, it is exactly that in terms of set theory. So,
I remember that homework.
Yeah, I do that on purpose. So if X and Y are topological spaces, and F is a function, let's say from, I'm going to be boring, the domain of F to X, to Y, where the domain of F is what? Some subset of X, all right? Then F is continuous if and only if what? Each V in the element of the topology of Y, right? I should say for each. It implies what? F inverse of V, right? You guys know what the inverse image of V is? Let me just remind you if you forgot. So this is X in X, such that what?
X is an element of V.
Yeah, f of X is an element of V. It's the set of points in the domain which map to V. It could be empty. Right. Now that has to be what?
And the topology of X.
Yeah, exactly. That's our way of saying it's open, right? So this is what's the definition of a continuous map is. Or as Manetti says, a map F from X to Y between two topological spaces is continuous if the pre-image, F inverse of A, is an open set. Of any open set is open. Right. He remarks that the operator F inverse from the power set of Y to the power set of X commutes with the operations of set complementation and union. So Manetti's dropping some knowledge on us here. Come on. This paperback book, sometimes very frustrating. Error. So, fun facts from set theory. The inverse image of the complement, all right, is equal to the complement of the inverse image. So these are some set theory, set theorems. Welcome to Math 200 if I ever teach it. All right, F inverse of union over I. I from where? What does the union over I mean in Minetti? Is that an arbitrary union or is that a finite union? Is that a countable union? Anybody read enough to know?
I certainly haven't.
Yes. I don't know. I mean, maybe Nate hooked you up. I don't know. I mean it's I guess you probably wouldn't accept that given your criticism of my glorious Indian text. This is some sort of act of economic terrorism on the fourth, third world countries. I just, well, anyway, I digress. Apparently. So this is union over I. How do you prove these sorts of things? Carefully, I suppose. It's usually just a matter. I mean, these kinds of things. I would be shocked if it's anything more than just picking a point and thinking through it. That almost always what these sorts of things are. I will foolishly attempt to prove this one, at least one of the directions. So we have to show that what? So half of this is to show that the inverse image of the complement is a subset of the complement of the inverse image, right? So let's let X be an element of F inverse of Y minus A, right? Then there exists what? Let's say Z in Y minus A such that what?
I thought X is equal to Z.
Right? But Z is not an element of A by definition of the complement, right? Therefore, what? F of X is not an element of what? A, right?
X is not an element of inverse A.
Oh, so hence what? X is not an element of F inverse of A, you say? Okay, and then what do I want to prove? I want to prove... Oh, I'm done.
You're done,
Yeah. Oh yeah, we're done. Okay, great. Yeah, so, yeah. I feel like there was some time in my undergraduate I spent 2 hours trying to do this and didn't get it done, but it's just sad. You should try to do these things with some amount of confidence and surrounded by people who actually know something. Right? All right, enough about that. What does this mean for us? As a result, a map is continuous if and only if the preimage of any closed set is closed. The preimage of any closed set in the codomain is closed in X. So it has to, the inverse image, in other words, in better words, this implies the inverse image of closed sets is closed for a continuous function. Do you see that? So if what would a closed set be? If V is closed, then what?
Y minus V is open.
Yeah, y minus V is open. Thus, F inverse of y minus v by continuity is what? Is open where? In x, right?
It's x minus, or x complement.
Yeah, but by the theorem that we proved half of. F inverse of y minus, I mean, we have to prove the other inclusion to complete the argument, right? Is equal to what? Oh. What? Oh yeah, sorry. X minus F inverse of A. Sorry, I mean, it's kind of, you could rewrite this a different way, right? Did you realize this? This could also be written, well, let me just stop before I say that. I've got some stupid computational nonsense comment to make, but, so the inverse image of this is, well that's open, but so that's open, right? So this, if this is open,
That means f inverse of v is
that means F inverse of A is,
what we were looking at.
why
v.
did I have A? Where did A come from? V, right?
Yeah.
Duh. So F inverse of V is what? It's
Close.
closed, yeah. And there you have it. V was arbitrary, so the inverse image of a closed set is, it's closed. All right. What I was going to say is, check this out. You can also look at this as this way. F inverse of y minus v, right, is equal to F inverse of y minus F inverse of v. This is true because the inverse image of y is x. That's not a proof.
Yeah, it can be.
It's just argument for notation is friendly. Let beta be a topological basis of y. A map F is continuous if and only if for any basis element in the set, the inverse image of the basis element is open in X. Okay, so in other words, you can check continuity. It suffices to check continuity on a basis. If we have a basis for a topological space, as we talked about last time, if you can check that the inverse image, the inverse image of each thing in the basis is open, you're good to go. It's another way to do it. And then, so of course, we want, some theorems about continuous maps. I think I will erase some of this stuff. That's okay with you guys. I learned my lesson.
Do the laser pointer trick with that again.
I did. Oh, you were there.
Yeah.
Yeah.
You can leave it in there.
Are you sure?
Yeah.
Something ain't right in that fridge. There's something wrong. Something really wrong in that fridge when I came back from vacation. I tell you,
That was right before
it's. I think maybe what was in there has been removed, but it lingers. It lingers.
Post really uses that like refrigerator.
I don't
Don't they have
know.
one? Don't they have one in the engineering department already?
Well, yeah, wasn't there the refrigerator in the break room down there? Yeah. I don't know. I'm very glad it's there. It's very handy.
Maybe someone's just trying to mess with you.
For
Maybe
me.
use your food.
Oh, somebody put some decaying rot in there just to bother me. I don't know. That would actually be. I would be impressed with that. I think that would be. I have to give them my. Anyway, okay, so let's try to list a few results here, Lemma. This is lemma 3.25. If we have f, and of course, if we have continuity for the whole space, I mean, I try to set up continuity for a subset, but often you just want to talk about, we usually just talk about maps from the whole space rather than from a subset of the space. I gave a definition based on a subset, like the domain possibly being subset, but usually we just talk about a mapping from the whole space, all right? So there it is. So this is a map between topological spaces. F is continuous. F is continuous if and only if what? F of the A bar is a subset of F of A bar for any subset of X. What's the bar mean? Ah.
Isn't it just complement usually?
No, well, why is he using, he's using minus for complement right before that. Your, I mean, I want to believe. Oh, it was defined on the previous page in a homework. The closure operator is a mapping from the power set to the power set, obeying the four Kuratowski axioms. So that is the closure operator. Exercise 3.15 says, prove for any topological structure on X, the map A maps to the closure of A, the so-called closure operator, is a closure operator rather, and conversely, for any closure operator C, there's a unique topological structure for which C of A is equal to A bar. What is A bar? Oh man, now I'm still left with the question, what's A bar?
I mean, hey, you got the universal property.
Goodness gracious. Eventually, the universal property. Oh, man, I was going to talk about that earlier. I'm a stooge. Duh. All right. We got to go back to the start of this. I see what happened here. Sorry, guys, I got distracted here. You know what? I'm not going to do that right now. I'll do that next time, maybe. I got to go back to the start of section 3.2 and talk to you about points being adherent, the closure, the interior. That's actually the boundary. The bar is the boundary. So that's the boundary. And I didn't really want to do that right now. So, which is bad because then I can't say that lemma. Well, we'll come back to it next time, hopefully. I'm actually going to go on and do other things that I think are fun, if you don't mind. Well, even if you do mind, I'm still doing them, because I think it's more important to say what I'm about to say than to get wrapped up in these technical points about continuous functions. We'll do that next time. Sorry about that. So, the big program in here is really, we have two topological spaces, X and Y, right? And if you've got a function that goes from one to the other, right? And suppose that this is a continuous function. if that's a continuous function, right, and it's a bijection, right, and if the inverse f inverse from y to x is also continuous, then f is a homeomorphism. Right. So continuous with continuous inverse is a homeomorphism. One of the, just as a side comment, really specialized side comment, if I have a linear transformation T, right, and it's going from one vector space V to another vector space W, and you could suppose that both of these are given, they're finite dimensional vector spaces, all right? And so essentially you can give them the metric topology. One of the really interesting theorems we proved is that if T is linear, right, that's extra structure, and T is a bijection, all right, so that theoretically all that would give you is that there exists an inverse map, right? But it's more than that. What we proved in linear is that the inverse map not only exists, but it is itself linear. So, linear algebra gives T inverse W to V also linear, right? And that's pretty cool because it's not too hard to prove that in the metric context a linear map is a continuous one. You can pick a basis, look at its matrix, find the maximum element in the matrix and play games like that to come up with estimates to show that it's behaving, it's not being discontinuous. So it's kind of funny. In the case of finite dimensional vector space, I would say that this is unnecessary. If the inverse exists, it's automatically continuous in this very nice, well-structured context. But in the wild world of abstract topological spaces, you do need to check the inverse for continuity. You're like, what's an example of that? That's a good question that I should be able to answer.
I was literally just about to ask that.
Let me tell you what, I will try to find an example of that for you guys, okay?
Example of help.
Other definitions while we're on this cavalcade of basic terminology. A map is said to be open if what? F is open. That means that F of an open set is open. So an open map maps open sets to open sets. F is closed. A mapping is closed implies that the image of a closed set is, you guessed it, closed. So the following conditions are equivalent. F is a homeomorphism. Assuming F is a continuous map, okay, the following are equivalent. F is a homeomorphism. F is closed and bijective. 3, F is open and bijective. So in other words, these two conditions, either one of them, implies continuity of the inverse.